Okay, so picking up where we just left off in our kind of preliminary discussion leading up to bonding, we have our Lewis symbols here that represent the valence electrons, or the electrons that are going to participate in bonding. And if you think back to chapter 2, we talked about ionic bonding. We talked about how a metal is likely to lose an electron when it interacts with a nonmetal, which is likely to gain an electron, right? We can revisit that process here by thinking about Lewis symbols. So a pretty standard ionic compound would be something like lithium fluoride, right? We should know at this point lithium is a cation here, so it has lost one electron compared to its neutral atom. Fluorine is the fluoride anion. It's gained one electron relative to its neutral atom. But if we think about this in terms of Lewis symbols here, right, our lithium atom would look like that, one valence electron. Our fluorine atom would look like this, right, 7 valence electrons. And the process of ionic bonding, we said, could be described as the transfer of electrons. So basically, this electron is moving from the lithium over to the fluorine, right? And that's giving us a lithium with no valence electrons, right? We've completely emptied out the second energy level, which would make that a cation. Our fluorine now has 8 valence electrons because it has that one extra electron, would fill up that second energy level. Excuse me, that would give it a negative charge, right? And this is really this separation, different charges, gives us this electrostatic interaction that holds our ionic compounds together, right? And of course, we would usually just write it as lithium fluoride, but all of this is sort of understood as to how this is happening, right? So this transfer of electrons is how ionic bonding works. Covalent bonding is a little bit more complicated, and we talked about that in terms of naming, right? That there are lots more options for the types of molecules you can get between certain elements when those elements are all nonmetals. So as opposed to ionic compounds where we know what the charges are on many of the ions, and so we don't put prefixes into names, like sodium oxide, for example, is Na2O. We don't call that sodium dioxide because we understand the charge on sodium is +1, the charge on oxygen is -2. That di is just adding more complexity to a name that doesn't need it if we have a basic understanding of how those bonds form. So that's just sodium oxide. But when we talked about something like nitrogen, right, we can make NO, or we can make N2O, or we can make NO2. We can't just say nitrogen oxide. We do not have enough information. So we use prefixes: nitrogen monoxide, dinitrogen monoxide, nitrogen dioxide. And that's because of the complexity of covalent bonding. And the reason that covalent bonding is more complicated in terms of structure than ionic bonding is because it doesn't work by transfer of electrons. It works by sharing electrons. So basically what we're going to try to do is come up with a method we can use to figure out how the elements involved in a structure are sharing their electrons to get to the point where the elements have more stability, right? Kind of like we did for ionic compounds. We're trying to get to that level of electron configuration that's similar to a noble gas. We're doing something similar here. Now, we're going to share electrons between our atoms, and there's a goal generally that we have in mind when we're sharing electrons, and this is often called, I'm going to put a little quote there because this is used a lot. This is often called the Octet Rule. So for the vast majority of elements, and particularly nonmetals, we're focusing in more on the nonmetals when we talk about this type of bonding, right? They all gain stability when they end up with a similar configuration to the noble gases. Well, in their highest energy level, just counting the S and the P sublevels again, these would all have 8 valence electrons because we've filled up that S and P sublevel. So the Octet Rule refers to this idea that if we get to 8 valence electrons, we have added stability. So that is kind of the goal in a lot of our drawing, is to try to get to 8 valence electrons. Now, hydrogen is also a nonmetal, though. Remember that. Hydrogen is a nonmetal. Hydrogen can't get to 8 because hydrogen only has access to the first energy level. So for hydrogen, we want to get to 2, right? Hydrogen can get to the point where it has a similar configuration to helium. So that is kind of a notable exception to the octet rule. Hydrogen wants to get to 2 electrons, right, which you could call like a duet of electrons for hydrogen. But for most of the other nonmetals, we're trying to get to 8 when we draw these structures. Okay, now the next bullet I have here on the front page is Lewis structures. That means I want to jump to the next page. So remember, we're coming back to this. Don't throw that away or get rid of it. We'll come back to some of the issues there when they pop up in our drawing of these structures. So the first couple structures here, I kind of want to point out what's happening in terms of a kind of a simplistic, cartoony sort of picture. But then I want to start to use them to work into a familiarity with the rules I mentioned in that other document. So hydrogen, the diatomic molecule, just H2, is made up of 2 hydrogen atoms. And if we take this picture of 2 hydrogen atoms and we imagine this duet rule we just talked about, right? Each hydrogen would have 1 valence electron. Excuse me. Yeah, let me grab a tissue real quick. Okay, sorry about that. So each hydrogen has a valence electron. If we keep the duet in mind, right, there'll be an added stability here if the hydrogens can share the electrons in a way where they each have 2 electrons. That would be satisfying that duet rule for hydrogen. So just from the picture here, we can kind of imagine, well, if this hydrogen offers its electron to share with this hydrogen, and this hydrogen does the same thing, offers up its electron to share, if they're sharing the 2 electrons, they both have 2, and they reach that added stability. Well, pictorially, the way we would represent that is we'd move an electron in from each of them to make a bond between the 2 hydrogen atoms. So the way we draw that is just with a line between those 2 atoms. And anytime we draw a line like that, it represents the sharing of 2 electrons. So hydrogen, the molecule, H2, has 2 electrons. If we share them between the hydrogens, we get a stable molecule. Okay. Now let's come back to that in just a minute, and let's talk about the rules on the worksheet that we can maybe look at and start to build up our ability to do that. But before we do that, let's look at chlorine over here as well, because there's a lot of similarities in what's going on with chlorine. 2 chlorine atoms, right, individually, not connected yet. But where chlorine is in the periodic table, we could see that each chlorine would have 7 valence electrons, right? Now, again, if we think about the rules we just talked about, if chlorine follows the octet rule, we want each chlorine to have 8 valence electrons. Well, we can get there by sharing this one odd electron. If I just move each of those electrons in like that, I can make a bond between the chlorines. So again, 2 shared electrons between the chlorine atoms. Now, each chlorine in this case has 6 electrons that are not shared, that just are part of the electrons around that individual chlorine atom. Those are often called non-bonding electrons, right? Or sometimes they're called lone pair electrons, because usually they remain paired up. We'll see a few examples where they aren't paired, but in this case, they're all paired. We could think of them as in an orbital with different spins, just like we talked about in electron configurations. But through that picture, we can get an idea of how a bond, covalent bond, can form between 2 chlorine atoms as well. Now, if we look back to that worksheet, the worksheet says, right, the first thing you do is you draw the skeletal structure of the compound. So with just 2 atoms, that means we're just connecting them. So with the first thing you do for hydrogen, we've already accomplished the structure, right? We got the same picture as we had up there. So draw the structure, right? The second thing you do is count the total number of electrons, right? We only had 2 total electrons for H2, but we already used them to make that one bond, so we don't have to do anything else there, right? So this is what, I want you to get used to using this handout, because this handout is kind of designed to always lead you through a process of steps that will get you to the right structure. Similar for chlorine, right? The first step, draw the skeletal structure. So that means we're going to connect the atoms with a bond. just two atoms, there's only one way to connect them with a line between them, right? If we count the total electrons on chlorine, we said each chlorine brings 7 valence electrons. There's 2 chlorines here, that would be 14 valence electrons. So the third step says, right, first step, draw the structure, we did that. Second step, count the electrons. Third step, complete the octets of the surrounding atoms. So we want to complete the octets around the chlorine. So we used 2 electrons here to make this bond. Out of the 14 we started with, that would be 12 left. That means I have 6 left I can put on each chlorine. And that gets me to the exact same picture, right? So this first this idea of, ooh, let's start with the Lewis symbol and push electrons in to share them. This is way too simplistic. This is going to work for simple molecules, but it is going to crash and burn if we try to look at more complicated molecules this way. So this is maybe a good way to start thinking about this, but this should not be a process you rely on to try to draw a structure, because a lot of structures are going to really not be intuitively derived from this kind of idea. That's why we have this separate list of steps to follow, right? They should get us to the same answer, right? But as molecules get more complicated, this method is not going to work. So I want you to think about the steps I'm describing, right? And try to work those into how you are drawing structures. Okay, we'll stop there, right? We'll come back to nitrogen and oxygen in the next video and keep working on applying this process.